Log on, tune in, find out. Another good idea from Cambridge.
Good morning, everybody, and welcome. There may be some of you for whom this is the first time that you've come to the Newton Institute. So I should say that I'm David Wallace. I'm the director of the Institute. It was founded in 1992, and we run research programs across the whole range of mathematical sciences, pure maths, and all its applications. And the current program, one of the current programs, is on algebraic Lie theory, and this is a Spitalfields Day as part of that. So I'm really grateful to the organisers, to Sasha, to Gerhard, and to Meinolf, both for organising the programme and for organising this day. Also extremely grateful to the London Mathematical Society, who provided some support, which I hope some of you have actually benefited from. For those of you, this is meant to be these lectures for a more general audience, so there may well be some early career researchers here. And I should mention, therefore, that for those of you that are within doing your PhD or in the first 5 years of your postdoc in the UK, we have a junior membership scheme, which we provide information to and which enables you to get into programs here. I think that's probably all that I want to say. And the program here looks really interesting. I'd love to sit in on it for my own education, but other duties, I'm afraid, rule that out. I have a quite specific request, please, to turn off your mobile phones, because as you may be aware that this is being videoed, and its ring will be recorded for posterity, so I'd rather that we're all switched off here. If you are going to, I do hope that you will interact with speakers to ask questions during as well as afterwards, and these will be picked up because you can see there are microphones here as well. So it looks a great program. Have a great time here and take full advantage of your day at the Institute. Thank you all very much. Now I hand over to Gerhard.
Right, welcome to your today. I'll announce the first speaker. I'm very pleased to have John Coates from the University of Cambridge. He'll speak to us on L functions and arithmetic.
Thank you, Gerhard. So let me get straight down. By the way, I'm afraid, well, I hope people can read these transparencies. Is that visible too? Yeah. So, in fact, let me get straight down to business. In fact, there are two main themes in this general area of L functions and arithmetic. One is classical analytic number theory, where you relate the distribution of zeros of L functions to asymptotic arithmetic questions. And of course, the classic example here is the Riemann hypothesis, that the Riemann hypothesis for zeta s is equivalent to this marvelous guess. Well, Gauss didn't make a guess as precise as that, but this marvelous guess of Gauss for the difference between pi x and Lie x. Now, fortunately, Andrew Granville covered all this yesterday, so I don't have to say anything more about this first case. And the second case is really the question of the exact formulae of number theory. The first examples, of course, were proven by Dirichlet, but the celebrated example today is the infamous conjecture of Birch and Swinnerton and Dyer. And of course, there are many generalizations of it, but I want to concentrate in my lecture today on that basic old conjecture. And I should say that in this connection between the two, there's always lurking in the background a motive. And you're really looking at the arithmetic of that motive, and we're trying to relate it to the complex L function of the motive. And in some cases, it might be a Tate motive. In fact, again, for my lecture, just for simplicity, I'm going to purely deal with the case when the motive is an elliptic curve defined over Q, for simplicity. And of course, let me just remind you that if you're a number theorist, and especially an old-fashioned one, you rely totally on the automorphic world, the experts in automorphic forms, to prove the analytic continuation and functional equation for the complex L function. And there's been some beautiful progress in that direction over the last 20 or 30 years, but still most, as we'll see it coming in later in my talk, many of the basic questions, of course, are still totally unknown. Now, in fact, I guess the main theme of the latter part of my talk is that the only general method we know at present for attacking this second type of exact formulae is passing to the p-adic world of Iwasawa theory. And so that's what I will be discussing. But, as I mentioned before, I'm going to take for my motive simply the special case, an elliptic curve defined over Q. But to motivate the type of question I want to discuss, let me begin by just recalling our current state of knowledge on the conjecture of Birch and Swinnerton and Dyer. So I have this elliptic curve E over Q, and I'm going to write GE for the rank of its group of rational points. There'll be a few invariants that will come up over and over in the lecture, and I want to keep that notation. The other object that we're interested in the arithmetic of the curve, of course, is the Tate-Shafarevich group, Shah of E, which is the kernel of you look at the global H1 of the Galois group of Q bar over Q acting on E of Q bar, and you look at the locally trivial elements in there. Now, there's a celebrated conjecture whose paternity is denied by many people, but in any case, it's a very classical conjecture now, that the Tate-Shafarevich group is always finite for every elliptic curve over Q. However, the truth is we only know it in some very special cases. And this, I want to come back to this example later on. If you take the curve y squared equals x cubed minus 17x, so it has GE equals 2. Its group of rational points is actually generated. These are two generators of infinite order, and this is generates the torsion on it. So we know exactly what the group of rational points is, but we do not know if the Tate-Shafarevich group is finite or not. And in fact, because of the conjecture of Birch and Swinnerton and Dyer, we'll come to that in a moment, we actually believe that Shah of E should even be 0 for this curve. In fact, another mysterious thing about the Tate-Shafarevich group is that it appears, especially for curves of rank bigger than 1, it appears nearly always to be trivial, although not always. And let me stress here that it's unknown whether the Tate-Shafarevich group is finite for a single elliptic curve E over Q with rank at least 2. We know no example where it's ever proven to be finite, or even weaker statements. So now, what do we know about Shah-E in classical terms? Well, there is this basic classical fact here, which comes out of a little bit of Galois cohomology, if you like, and abelian class field theory, that if you look at if you take any prime P and you look at the P primary part of the Tate-Shafarevich group, then there are a finite number of copies of QP mod ZP which turn up there. In fact, I need this invariant TE of P later on, so let me just write it up here. So this is the P primary part. So it's a certain number of copies of the divisible group QP mod CP plus a finite group. But the whole nightmare, of course, that we haven't been able to answer yet is that this is where the process of, if there really were examples where T of EP is positive, then the process of infinite descent would never terminate and we'd be in Rat's Alley. So of course we do expect that T of EP should be 0 for every prime P. That's what we certainly conjecture to be true, but in fact if you look at classical methods, they only allow you to calculate PE, I think at most for primes up to 11, the TEP, and if you try and give a everyone, if you read in all the books, they say classical methods, and it's true, they do give some sort of an upper bound for T of EP. But in fact, no one has ever bothered to write down that bound simply because it's so bad. It would be at least P to the P to the P to the something. Very bad bound. So up till now, I've been talking about the arithmetic of my elliptic curve without mentioning L functions. And of course, the marvelous conjecture of Birch, Swinnerton, and Dyer precisely relates these to L functions. So I'm writing LE of S for the complex L function of the elliptic curve. And here, happily, the automorphic world, thanks to many people along the way, tells us that in fact, in this case, LE of S is entire and satisfies the standard functional equation relating the values at S and 2 minus S, which I'm not going to bother to write down. So everything is happy from the complex point of view, and we can look now at this very interesting invariant, which I'm going to call R of E infinity, which is the order of 0 of this L function at S equals 1. And here is the, slightly imprecisely, but it's perfectly good for our purposes, the conjecture of Birch and Swinnerton and Dyer. Firstly, it asserts that G of E should be the same as this order of 0. And secondly, it gives you an exact formula for the order of Char E in terms of this coefficient of S minus 1 to the RE infinity. An exact formula which you can work out for any curve. If you work it out for the curve I wrote down, you get 1 for the order. So what do we know about the conjecture of Birch, theoretically about the conjecture of Birch and Swinnerton and Dyer? Well, the main theorem is this theorem here that I've written down due to Gross, Zagier, and Kolyvagin. And it tells us that if the L function vanishes at S equals 1 to an order at most 1, then in fact the order of 0, the rank is equal to the order of 0, and the Tate-Shafarevich group is finite. So this is a very beautiful, very deep theorem. And I won't be saying anything more about it, except to say that unfortunately the method of proof completely breaks down if the L function vanishes to an order bigger than 1. And the reality is that when the order of the 0 is bigger than 1, we actually know no way at present of relating E of Q and Char of E to the complex L function. It's sort of embarrassing, but we don't. Of course, numerically it's been checked almost ad nauseum, that the numerical evidence in favor of the conjecture of Birch and Swinnerton and Dyer is enormous, but the theoretical evidence, once the order of 0 is bigger than 1, is non-existent in hard terms. So in some sense, all that I sort of want to talk about in the rest of my lecture is motivated by this fact that we can hope to say something if we go to the p-adic world. And it turns out this somehow throws up many other interesting questions and problems along the way. So that's what I want to talk about now, but I want to, it's important even for proving things over Q, I'll come back to that later on, I want to state it, I want to describe Iwasawa theory in a, not in its classical form, but in a slightly more general form. So, of course, what it is, if you look at Iwasawa, he was totally motivated by trying to find an analog over number fields of the sort of basic work, Hasse, Grothendieck, which recovered the L functions of algebraic varieties over finite fields from their étale cohomology. And Iwasawa had the idea that if you looked at the classical theory of cyclotomic fields, you could actually find a number theoretic analog of that. And that appears to be true in great generality today, and that's really what my lecture is about. So, to do Iwasawa theory, I want to tell you what the ingredients I'm going to take. They're not quite the most general that we know something about at the moment, but they're close to the most general, except I'm always going to take my motive to be an elliptic curve. So first we have to pick a prime number p. And in fact, there should be a good theory for every prime number p, but later on we'll see that we only know how to formulate it under certain conditions on p. And I'm going to write mu p infinity for the Galois module of all p power roots of unity. And similarly, so E will always be my elliptic curve over Q, I'm going to write EP infinity for the Galois module of all p power division points on E. Then in addition, I'm going to define Q cyclotomic, the cyclotomic ZP extension of Q, to be the subfield of the unique subfield of Q of mu p infinity, whose Galois group is isomorphic to ZP. So this is all very standard notation. But now, so let me draw a picture of this. I now want to take an extension, a big infinite extension of Q. Let me write it over here. So I'm now going to fix for the rest of the discussion, and then we'll talk about the general discussion. We'll come back to some particular cases after. A Galois extension, which I'm going to call F infinity of Q. And I make three hypotheses of it. In particular, I always want to assume that it contains the cyclotomic ZP extension of Q. And the three conditions, which I'm going to explain now, that I want to impose. So I'm going to write G for this Galois group here. The three conditions are the obvious ones, more or less, apart from the cyclotomic extension being contained in there. Namely, that I want this G, this Galois group here, to be a p-adic Lie group. So maybe that's the only excuse for me talking today. It has something to do with some aspects of Lie theory. Secondly, of course, I want F infinity to be unramified outside a finite set of primes. Of course, this is always true if it's comes from étale cohomology or something like that. So I always want that, the second condition here. And thirdly, that I do always want it to contain the cyclotomic ZP extension. So in other words, this means that my p-adic Lie group G has a closed normal subgroup H, and the quotient G mod H is isomorphic to ZP. We often write this gamma, that's that Galois group there. So there are lots of examples of such extensions that turn up in nature. Of course, you could take the field of all p power roots of unity over Q. You could take the field that you get by joining to Q all the p power division points on your elliptic curve, or an abelian variety if you want. Or another interesting extension, which has a nice parameter in it, the m here is an integer bigger than 1, you could adjoin all the p power roots of unity to Q and all the p power roots of this fixed integer m. These are all examples, and of course there are many others that you could take. So, I keep forgetting the bottom. So what is the main idea of Iwasawa's theory and the so-called main conjectures? It's simply the following, that there's one, so you look at this group G, there's one p-adic representation of G which simultaneously encodes information on, firstly, the arithmetic of E over F infinity, and secondly, the special values of all the relevant complex L functions. That's what Iwasawa theory is all about. And the whole idea of a main conjecture is to make that precise. So let me begin slowly to make it precise. So I should first explain what the relevant L functions are for us. And they are the following. So you see what I look at now is the set, which I'm calling A of G, of all irreducible Artin representations of G. So by an Artin representation, of course, I mean one that factors through a finite quotient. And so we can think of it as realized over the complex numbers or over QP bar as we wish. And then you see if you take one of these Artin representations, you can then twist the complex L function of the curve by the representation. It's a very classical procedure. And so this is, in fact, if you want to formally define it, it's the Euler product. You take the H1 of the curve and you tensor it with, of course, when I say rho, I mean the underlying vector space of rho, and you take the Euler product attached to that. Now, the first problem is that, unfortunately, our friends in the automorphic world cannot prove the analytic continuation of these twists, even though when it's the trivial character or character of dimension 1 they can, but in general, it's only in some cases that we know, very limited cases, that we know the analytic continuation and functional equation for these twists. But I'm just going to assume that we do know it in all that follows. And then I'm going to introduce, so remember R, maybe I should write it here, RE was the order, infinity was the order of 0 at s equals 1 of LE of S. I can do exactly the same thing with my rho. I can look at RE rho infinity, which is the order, I want to come use this later on, at s equals 1 of LE rho S. So these It's this special values of these functions at s equals 1 that we're going to use to make a main conjecture. So then I should say, those are the complex L functions. What is the p-adic representation of G we're interested in? Well, it is the classical so-called p-infinity Selmer group. Let me just recall its definition. Special case of its go back deep into history. So you look to define this Selmer group, you now look at the H1. So I'm going to define it over F infinity. I could be taking any over any extension of Q here. But now you look in the H1 of the Galois group of Q bar over F infinity acting on EP infinity, and you look at the locally trivial elements in there in the sense that they go to 0 in the H1 locally of all the points. So this is a discrete, this Selmer group is obviously P primary because I've got P infinity here, and it's convenient to work with its Pontryagin dual. So X of E over F infinity will be the Pontryagin dual of this Selmer group. And the point is that both of these are endowed with their natural action of G because the curve is defined over Q. So no, I'm talking about any example. No, but I mean, this is G acts on this, and it clearly preserves the local conditions. Like, no, everything's. Doesn't matter which example you take. There's a natural action of G. And in fact, because, if you think about it for a moment, because this action is continuous, you actually have an action of the so-called Iwasawa algebra. Namely, what you do is you look at the finite quotients, G mod U, and you take the projective limit of their ZP group rings. So in fact, they are both, and because of course G is in our case not at all necessarily commutative, when we talk about a G module, we mean a left G module. So this is the relevant representation, and now we have to think how we can somehow make a precise statement, a precise conjecture, and one that we can test numerically, not anything vague, linking these two rather disparate mathematical objects. And it's not, I have to say, it's not obvious how to do that. In fact, we don't know how to do it in general at present. We only know how to do it, as for reasons that I'll be explaining now, when E has potential ordinary or multiplicative reduction with P. And it's a very interesting question how to formulate this for E's which are potentially supersingular. And it'd be the same with any other motive. So to explain how to formulate it, I have to tell you some rather curious algebraic facts about this interesting non-commutative ring lambda of G. In fact, it's sort of striking that if you look at the beautiful book of McConnell and Robson on non-commutative algebra, they talk about every non-commutative ring except the Iwasawa algebra. And it somehow has some of the most interesting properties, I think. And in particular, I want to, you see, it's our search for making a precise statement which leads one to look at this set S that I've defined here. So remember, because H is a subgroup of G, the Iwasawa algebra of H, lambda of H, is actually a subring of lambda of G. So if you look now at all the S in lambda, by the way, G is not necessarily pro P or anything like that. Lambda of G in general will have lots of zero divisors and so on. But now what we look at is the set of all elements in lambda of G such that the quotient lambda module lambda G over lambda G times F is a finitely generated lambda H module. And by the way, it would be this, well, okay, don't let me make a comment. So that's what we look at. And then it turns out, it's sort of totally elementary to prove it, but it's not quite obvious, that in fact, this S is an OR set in this non-commutative ring of non-zero divisors. And why that's significant for us is, so you know, in a non-commutative ring, you can't localize with respect to every multiplicatively closed subset. The localization doesn't exist. You need this additional condition called the OR condition. And usually if you look at, again, in the literature in non-commutative algebra, they have to use a lot of machinery to prove something is an OR set. Whereas here it really is a very elementary argument. By the way, this is, in some sense, was first proven in a joint paper with 5 authors, Fukaya, Kato, Sujata, Venyakov, and myself. So in fact, we're going to use this. It's crucial for us. But in addition, we have to throw in one more. You see, if you took it lambda G over P times lambda G, it's certainly not finitely generated over lambda H. But we need to throw in the powers of P there because of this phenomena in Iwasawa theory of so-called positive mu invariant that I probably will say nothing more about. So we actually enlarge it and throw in, look at this set S star, which you would join all the powers of P to the set S. Then what we're going to be interested in is the category that I've defined here called MH of G. It's the category of all finitely generated lambda G modules such that the quotient of M by its P prime, this is the submodule of all elements killed by a power of P, we want this quotient to be finitely generated over lambda H. So that's the category MH of G, and now it's an easy exercise to again show that in fact that's exactly, to belong to the category MH of G is exactly equivalent to saying the module is S star torsion, that every element in it is killed by some element of S. So in fact the modules in MH of G are all torsion modules over the Iwasawa algebra, but it's a much smaller category than the category of all torsion modules. So once we have this OR set, that's S star is again an OR set, then in fact we can localize, because it's an OR set, the localization of lambda G with respect to S star exists. So that's what I mean by that. And then it's been long known for 60 or 70 years that algebraic K theory provides us then with a canonical surjection of K1 of this non-commutative localized ring here onto the Grothendieck group K0 of the category MH of G. There's a very classical fact, which I guess goes back to Swan or someone like, I mean, perhaps not quite in this generality, but this is the sort of beginning of the localization sequences of K theory. And so in particular, and by the way, it's not quite obvious, this map is not always surjective, but in this case it's easy to prove it is always surjective. So if we have a module in the category MH of G, it's obvious what we should do now. We should define its characteristic element, or a characteristic element, to be any element of the K1 which maps to the class of the module under this homomorphism. And it's this simple algebraic fact which is now going to enable us to make a precise conjecture. So let me return now to the arithmetic situation, and I now want to make, again because I want to be precise, a slightly stronger hypothesis, namely that E actually has good ordinary reduction at P, rather than being potentially ordinary. And then the conjecture, again, everything I talk about here is in this 5-author paper. The conjecture that we make is that if you are in this situation here, that this representation given by the Selmer group, this module, is always in the category MH of G. Now, in fact, one can prove that in many cases. I haven't got time to, but there's the sort of obstruction to proving it in general is that there is this mysterious mu invariant which turns up in the Iwasawa theory of elliptic curves, and this conjecture is very closely related to comparing two different mu invariants, two mu invariants for different p-adic Lie groups, namely the one coming from here and the one coming from here. So I won't go into it any further, but in many cases you can prove this, including many nice numerical examples. But we don't know how to prove it in general. So granted this, now let's assume that our module is in MH of G, then the main conjecture will say, and again I'm going to make it more precise, that we can find a characteristic element of this module in the K1, which is a p-adic L function. That will be the main conjecture. So I have to explain to you now what we mean by a p-adic L function. That will bring us back to the complex L functions. Well, lurking behind this, you see, is this, again, not entirely trivial algebraic fact here that I should mention, that if you have any element of this K1, then in fact, and you take any Artin representation, in fact, you can evaluate this psi at that representation. And you get a well-defined element of QP bar. Let's assume the representation is realized over QP bar. And, or you could get infinity. You see, this is not entirely obvious because of the reason that there's no, well, it's not entirely obvious for many reasons. You'll see it explained in detail in our paper, but you can do it. And so now the idea is that this p-adic L function that we want to take its values at the Artin representations will be essentially these values of the complex L function at 1. But let me be again quite precise because I don't want to wave my hands as to what exactly the values will be. So the first thing I want to say is that I have to throw away the primes which are different from P and whose inertial subgroup in this p-adic Lie extension is infinite. I don't care about the primes where there's only a finite number of ramification, but the ones where the inertial subgroup is infinite, I all put them inside T, but not the prime P. And then I have I look at the Néron differential on the very good global model of the curve, and I have it's two periods. This is the real period omega plus c, and this is the one on which complex conjugation acts like minus 1. And then because I'm assuming that my curve has good, so this is the Euler factor, so to speak, of the complex L function of E, and because I'm assuming that it's good at ordinary reduction, one root will be a p-adic unit and the other will be a non-unit. So I'm going to write U for the unit root. And now the whole idea is that I'm going to now look at the Artin, I'm going to vary my Artin representations for this p-adic L function. And for that I need some other invariants which are related to the representation row. Namely, if I look at if I pick a vector space over, say, QP bar on which the representation is realized, complex conjugation will act on it, and so I can take the dimensions of the subspaces which it acts like +1 and -1. So that's these two integers here. This p to the f rho will denote the p part of the Artin conductor of rho, and epsilon p of rho will be the local root number at p of the representation rho, not of rho tensor the curve, but of rho itself. And finally, pp rho x will be the Euler factor at p of the Artin L function L rho s. So not Le rho s, but the Artin L function. So now what the conjecture is that the general main conjecture in this situation is that there does exist an element in the K1 of lambda G S star. Well, sorry, it's not the main conjecture, it's the conjectural existence of p-adic L functions, such that if, as you vary your rho over the Artin representations, these values are never infinite, there's no pole in this situation, and that the exact value should be what I've got here, namely, this is now the Euler product of Le rho s, but you throw away the primes in T. You divide by these periods to these exponents, and then you have to do this modification here, which somehow is related to the Artin L function, namely you multiply by EP of rho, and then you put in, and by the way, W is the non-unit root of the p-adic L function, and then you take here U to the minus F rho. So I mean, it is really an exact formula, and in fact, when we first tried to formulate this conjecture, I have to say we got it wrong, the formula. And it was only thanks to the Dogchitzer brothers doing some numerical calculations for us that we were able to realize it was wrong, and after several days of thinking the universe was collapsing, we realized you had to take this formula and everything was right. So now, by the way, I should say that in the sort of genuinely non-commutative case and an elliptic curve, we still do not, when G is say, of dimension bigger than 1 and it's non-commutative, we still can't prove the existence of this p-adic L function when the motive is an elliptic curve in any new case, but in any case. But if you take the Tate motive, then in fact there's some beautiful work being done recently by Mahesh Kakde where he proves it exists for the Tate motive in the non-commutative case, subject to certain conditions. Anyway, it's obvious now what the main conjecture should be, namely that the boundary of this p-adic L function should be the class of the Selma group. That gives the precise link between the L values and the arithmetic. Now, I should say that in fact, I'm going to talk about some specific consequences, but in general, you see somehow these just make one mark in general before I get down to it, but to more specific things, that you see all of these exact formulae of number theory are really statements about the G Euler characteristic of this module, and perhaps its twist by Artin characters. Everything can be interpreted as Euler characteristics. And in fact, this formula you can easily show is perfectly adapted to dealing with that. And things like the exact formula of Burt, Swinnerton, and Dyer, and so on, all follow by somehow analyzing it more carefully. But now what I want to do, I only have 15 minutes left. I want to talk about some specific applications that you can actually get. So this is a completely general conjecture. The truth is we know it only in a very limited number of cases so far, but I want to talk about the theorems that do come out of it, that we can actually prove about the arithmetic of the curve over Q from what we know at present. And the first one is this theorem here. I mean, again, special cases of it are due to many people along the way, but what you can show easily, so we're always assuming, by the way, that P will be, for this discussion, a good ordinary prime. And so what you can show is that if GE is positive, if there is a point of infinite order, or if the TE of P, right, that's the number of copies of QP mod ZP here, is positive for even a single prime P, then in fact the complex L function must vanish at s equals 1. This is somehow the easy thing to prove from it. By the way, remember, we don't know at present that if G equals naught, Shah is finite or anything like that. It's only if we know something about the complex L function that we can make such statements. So this is... Now the second thing I want to talk about is this invariant TE of P that turns up here, which, let me remind you, of course we want to show it's 0 for every P. But you could ask, granted we can't do that, for the more modest desire of just proving an upper bound for it, and particularly an upper bound for very large P, as P goes off to infinity. And there is one such result that it turns out to be fairly easy to prove in this direction, granted the Iwasawa theorem. And I'll say a little bit about how you prove it. And it's this theorem here, which is proven with two collaborators, that let's suppose that E has complex multiplication. Unfortunately, we don't know how to prove this theorem for curves without complex multiplication present. And let's take epsilon to be any positive quantity. For example, epsilon equals 1, but whatever you want. Then for all sufficiently large good ordinary primes P, you can prove that the TE of P, this integer here, is at most 1 plus epsilon times P minus the rank. So it's a very, very weak result, but it doesn't seem possible to prove anything like this without somehow without the full force of the main conjectures of Iwasawa theory. And by the way, this is a theorem. It doesn't depend on any unproven hypothesis. So now I want to say a little bit about the proof of this theorem, because it illustrates why the whole situation is different in the p-adic world. So I'm assuming that But by the way, again, that theorem, I should say, we have no idea how to prove it at present for the supersingular primes for your curve. It's again just for the ordinary primes. But so I'm assuming E has complex multiplication and that P is a good ordinary prime, and then we're going to use this big theorem of Rubin and Jaeger that, in fact, now it's slightly weaker. I don't want to go into that now. It's actually what we know is slightly weaker form of the main conjecture that I stated, but it suffices for our purposes. That the main conjecture is true now if you take this field F infinity equals Q adjoin EP infinity. That we actually know, of course, that by the way pairing this contains Q adjoin mu P infinity. We're in this situation here, and the main conjecture is true. Then you see, and by the way, there's a p-adic Lie extension of dimension 2, of course, in this case, because it has complex multiplication. Now, what it turns out to carry out the argument is you don't work with the whole of this p-adic L function, which exists in this case, but you only work with a certain branch of it. That, in fact, it's related, it's the branch related to a certain subfield in here whose Galois group has dimension 1 over Cupid as a p-adic Lie group. But let me, I don't have time, let me not be precise. So there is a branch, and then as a corollary of the main conjecture, so let me write, so S now is, of course, a variable in the p-adic integers Zp. This is a nice analytic p-adic function. So I can write Rep for the order of 0 at S equals 1. And then it's sort of almost obvious from the main conjecture, but impossible to prove any other way. You can prove that in this case, in the p-adic world, this Re of P is at least the rank of the curve plus TEP. You see, this is precisely what we cannot prove in the complex world. We can't prove that Re of infinity is at least G of E. That's the whole problem. Let alone anything involving the Tate-Chafferet. In the p-adic world, this is essentially obvious. And then, you see, to finish the proof, this is strange. I've lost oh no, here it is. So to prove the theorem, all you have to do is to show that this order of 0 of the p-adic L function has a nice upper bound. And in fact, it turns out to be fairly easy to prove theoretically that the order of 0 is at most 1 plus epsilon p when p is sufficiently large for a good ordinary prime. So if you just combine these two, you get the theorem that I stated. Now, I want to just mention too that these main conjectures are very powerful for numerical calculations. And I just want to illustrate this by an example. So remember I said at the beginning that classically you cannot compute, even with our best computers. You can't do more than the p primary part of SHA up to about 11. But if you accept this p-adic, let's go back to this curve which has been bothering us. And here, y squared equals x, its GE is 2. The ordinary primes, of course, the good ordinary primes, this complex multiplication by z of I, are the primes congruent to 1 mod 4, and I have to throw away the bad prime, 17. So what you can actually do by in fact, you see so we've proved numerically by doing numerical calculations that the p primary part of the SHA of this curve is indeed 0 for all primes like this up to 29,700. And 29,700 is purely dictated by when Liang's laptop ran out of memory. And the way in which you do that is that you prove that this invariant REP, you can prove numerically that it is indeed equal to 2, as you'd expect for all the primes up to there. And then then it turns out, by the way, that it's like Bergsmith and Dyer, that this p-adic, you can then read off the order of the p primary part of SHA from looking at that expansion of the p-adic L function. Okay, so that's one direction that you can look at. Now I want to quickly mention two others. The first is that strangely these purely p-adic main conjectures seem to imply something very strange about complex L functions. And I now want to quickly mention that. So let's return, again it appears to be completely general, to our general p-adic Lie extension, F infinity, containing Q cyclotomic. And I want to now write chi for the set of all one-dimensional characters of the Galois group of Q cyclotomic over Q. So obviously chi is a subset of A of G. They're all Artin representation, irreducible Artin representations of G. And then, in fact, the following rather mysterious conjecture appears to be true, with this completely general setting, that there does exist, given my p-adic Lie extension and my curve, that there exists a constant Cp E over F infinity depending only on P, E, and F infinity, but not on the Artin representation rho, such that now, remember this RE rho infinity is the order of 0 at s equals 1 of the twisted complex L function. And it's, firstly, the conjecture is that this is always finite, which is not obvious. And secondly, that it's bounded above by this uniformly, by something which is independent of rho. Now let me say that when F infinity is actually equal to the cyclotomic, or even a finite extension of the cyclotomic ZP extension of Q, this conjecture is actually a very interesting theorem of David Roehlich, proven analytically. But why we believe it's true in general is that, in fact, in a paper by, I've run out of time now, but by Fukaya, Kato, Sujata, and myself, we obtained some strong evidence for it for this p-adic Lie extension here, where you join all p power roots of unity to Q and then the p power roots of some fixed integer m. And what's surprising, and I believe it's true in general, is in that case we come up with an exact formula for this Cp of E over F infinity, that you can actually work it out exactly. And what's really striking is that the dependence on this variable integer m seems unbelievably strong. I challenged one of the analytic number theorists to get even anything vaguely near that, and it seems very strange, this formula, but there it is. And in general, the p-adic world of Iwasawa predicts an exact, well, it looks as though it predicts, and it really does in this case, an exact formula for this constant that you can work out for your p-adic Lie extension. Now I have 1 minute left, and I want to raise another issue, where we can't prove anything but accept some rather indirect evidence. But you see, it's sort of everything about these complex L functions, LE of rho S, appears to be reflected in these Iwasawa modules. And you can push that. I mean, you can study global root numbers, things like this. You can do a lot in that direction. But one can't but help wonder whether or not the local root numbers. So now well, by this, I mean with the E in here as well. I should write EQ, E rho. That the local root numbers, where now rho runs over A of G, can you find a formula in terms of these local Iwasawa modules that I haven't really talked very much about, but which turn up in the analog when you study the Selma group a little more carefully? That it seems very probable that there is such a formula, and that somehow these strange phenomena that we again study in this 4-author paper should be much more easy, about global root numbers, should probably be more easily understood if you could do that. Thank you very much.
Any questions or?
Can you say something about the uniqueness of the periodic L?
Yeah, we don't know uniqueness, Tony. But presumably it should be true. But from that interpolation, you see, it might be to get uniqueness for a general periodic Lie extension, you might have to look at twisting by non-Artin characters, I suspect. But the truth is we don't know. And of course, for the main conjecture, you don't care whether it's unique or not.
Except a different one.
Right, but I mean, if they all have those L values, somehow the arithmetic would never see the difference. But I believe it is unique. It's just we can't prove it.
Thanks very much.